Okay, so to evaluate that first exponential sitting on the state, remember that x dot p, what will this be? Well, this will be x naught p naught minus x dot p, and this is t times by the Hamiltonian minus x dot p. This state is an eigenstate of the Hamiltonian and the momentum. So all that happens is we get the eigenvalues plugged into the state, okay? So if we've got k1 dot 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 up to kn, what this will be e to the minus I. We will have t, then we'll have a sum from I is equal to 1 up to n, and we've got omega ki. So I've plugged in the eigenvalue for the energy. Remember, when the energy acts on the state, it's just the sum of the omegas. And then we'll have plus I. You see, we multiply by minus I. So that's why the sign of the tx term has changed and why the sign of the x dot p term has changed. And then we've got a sum from I is equal to 1 up to n. And we've got an x dot k acting on the state, k1 up to kn. Now, if you are not sure why the eigenvalue just plugged in, well, remember what we said. If you've got a function of the operator, here we've got an exponential of the operator, that function is always defined in terms of a power series expansion, and you just plug the operator into the power series expansion. So do that, allow it to act on the eigenstate, and you'll see that everywhere where the operator appears in the power series expansion, it's replaced by its eigenvalue. And then if you just resum it, the function is now just evaluated at the value of the eigenvalue. Good. So you just plug the eigenvalue in. All right. So if we now take e to the ix dot p alpha k dagger e to the minus ix dot p on this function. So what is this equal to? Well, this is e to the ix dot p alpha k dagger, and then we've got e to the minus it sum from I is equal to 1 up to n of omega ki. This is what we just derived, plus I sum from I is equal to 1 up to n of x dot k. Good. And then we've got the state, k1 up to kn. Now, what sits here in the exponential is just the number, so I can pull that number out. Let me pull it out to the front. This is e to the minus it, sum from I is equal to 1 up to n omega ki plus I, the sum from I is equal to 1 up to n of x dot k. And then I've got alpha k dagger acting on the state, okay? When alpha k dagger acts on the state, all that it will do is create a particle of momentum k. So now if I act with e to the ix dot p on the state, well, I again plug in the eigenvalue, but remember, the energy has changed now. The energy was the sum of all of the energies, but we need to include the energy of the last particle k that's been added. And the momentum has changed because we need to include the momentum of the last particle k. So what we have is, we have e to the minus it sum from I is equal to 1 up to n omega ki plus I sum from I is equal to 1 up to n x dot ki. And then for the e to the ix dot p, we will have e to the it sum I is equal to 1 up to n of the omega ki, but then plus it omega k. So that's from the extra particle that was added. Then from the momenta, we have minus I sum from I is equal to 1 up to n of x dot ki. And then we have minus I x dot k for the extra particle that was added. And this is now all multiplying the state ket k1 to kn and with k added. Now notice something. In the exponent, this minus it term will cancel against this it term. These are all just numbers, so you can multiply them as usual. And this ix dot ki term cancels against this. Oh, I got the sign wrong. Okay. Will cancel against this. Sorry. That's a plus. Oh, I got the sign fine. We'll cancel against this term at the minus I. Okay. So what do we land up with? Well, this is, oh, let's change it back to black. This is e to the it omega k minus I k dot x k1 up to kn and k. And now there's just one more rewriting I want to do, a very simple rewriting. I want to say that this is e to the it omega k minus I k dot x alpha k dagger on k1 up to kn. Now I want you to notice something. What we have here is any state of a basis. Okay, this is any state in the basis. Any state in the basis. So the first line is an operator acting on any state in the basis equals the last line is an operator acting on any state in the basis. Now look at the first line. The operator that's acting does not depend on K1, K2, or up to Kn. Look at the last line. The operator that is acting doesn't depend on K1, K2, all the way up to Kn. So what that means is the operator acting on the state in the first line has to be equal to the operator acting on the state on the last line because they are equal acting on any basis. So we learn that e to the I x dot p on alpha k dagger e to the minus I x dot p is equal to e to the it omega k minus I k dot x alpha k dagger. Just by the way, while we're here, notice that if I was to dagger this equation, I can now get immediately a second equation, not for alpha k dagger, but for alpha k itself. Okay, so why don't you try to dagger this equation now, see what equation you get for alpha k, pause the video. Okay, good. Now let's do it together. So if we see what happens, if we want to dagger this equation, well, the operator that's last must come first, so it'll be an e. The minus I complex conjugates to an I, x dot p. Then we'll get alpha k dagger, which daggers to alpha k. And then the operator that's first, e to the I x dot p, that daggers to e to the minus I x dot p. This is equal to, daggering means we must complex conjugate, so we get minus I t omega k plus I k dot x. Then we need to dagger the alpha k dagger, that just gives us an alpha k. All right, so we've got those two equations telling us how this operator acts on alpha k and alpha k dagger. Good. Now, let's come back to this equation. Where was it? This was the equation that we wanted to solve. So let me just grab this. Good. Let's duplicate that. And now let's take it downstairs. Okay. And let's see what this tells us. Good. So that's the equation we want to solve. And we can immediately say that, we can immediately say that fk star of x alpha k dagger is equal to, now we've got fk of naught, that's a start, and the e to the I x dot p alpha k e to the minus I x dot p is just e to the I t omega k minus I k dot x alpha k dagger. So actually, what is this telling us? Well, it tells us that fk star of naught is equal to fk of naught, okay? But I'm just going to call fk star of x. Then here's fk of naught, but that's just some constant. I don't know, let's call it ck, just some constant that depends on k. And then we've got e to the it omega k minus I k dot x. And that means we have completely fixed the x dependence of our function fk star. And if we simply complex conjugate that, what do we learn? Well, we learn that fk of x is equal to, actually, I'm going to call this one complex conjugate, okay? This will just be ck e to the minus it omega k plus I k dot x. So we've actually determined completely the x dependence of our field as we said that we would. Okay, so let's now plug this in. By the way, let me write this in a slightly nicer way. This can be written as ck star e to the I k dot x. So just check that that exponent is the same as that one. And this can be written as ck e to the minus I k dot x. Okay, and just check that that exponent is equal to that one. Okay, you know enough to check all of that, so certainly you can check that. Okay, so let's now add this in to our field. So here's our field sitting over here. Let me do this. Good. So we've finished solving A3, and let's determine the x dependence of these functions. So let's put the x dependence in. So there was a constant ck, there was an e to the minus I k dot x, and there was a ck star and an e to the I k dot x. And just to be completely explicit, k dot x is equal to omega kt minus k dot x. Great. Okay, we will continue in a moment.